Today I'm going to talk about a paper that I just found on arXiv today, learning from others' mistakes, avoiding dataset biases without modeling them. This is an exciting paper because this paper proposes to automatically let the models avoid the mistakes from a weaker model. So their motivation is that the models with limited capacity, a weak model, primarily learns to exploit the biases in the dataset. So they want to train a main model that performs well on a dataset but avoids the biases that is captured by the weaker model. So they set up a product of experts setting and optimize the main model while fixing the parameters of the weak model. So they can optimize the main model in a good way while bypassing the need to handcraft the biases that to specify. So they don't need to specify the biases that is captured in the weak model because the weak model with a very small capacity automatically captures the bias. So how do they set up the product of the expert? They set up using this equation 2. So when they set up this loss, they're able to encourage the gradient updates of the main model to be different depending on the values of the weaker model. So they plot in figure in figure 1a, they plot the gradient updates for m. So when W is large in magnitude, which means it's certain, but when it's negative, which means it's incorrect, then this corresponds to the blue region where we can see the main model's parameter updates are large in size. So this encourages the main model to receive the gradients more aggressively. So on the other hand, when the weak model is certain, large in magnitude but correct, which is positive in size, positive in sign, then this corresponds to the green area in figure 1a. The parameter updates of the main model is negative, so the main model is suppressed in this case. So in the third case, when the weak model is uncertain, as an example in the red area, which they take W to be 0, then the product as expert cross entropy loss is just equal to the cross entropy loss of the main model. So you're basically updating the main model according to this setting. So in this way, the main model is updated differently depending on how confident and whether the small bias model is correct or not. So they did experiments on several data, synthetic experiments, and analyze and QA data. We found that when the majority of the training examples contain the bias, then the performance of the model trained with cross entropy drops faster than the one trained in the product of experts. So product of expert training leads to a more robust model by encouraging it to learn from the mistakes of the weak learner. On multi-analyzed hard test set, the proposed method surpasses the performance of a product expert trained with a hypothesis-only biased learner. They also discussed how weak do the weak learner need to be. So in figure 4, the weak learners assure a good balance between out-of-distribution and in-distribution, while stronger learners encourage out-of-distribution generalization at the expense of in-distribution performance. They depict the capacity of the learner with the number of parameters, and the number 4.4, 11.2, 28.8, and 41.4 are in unit of millions. So they presented an effective method for training models robust to the dataset bias. They discussed the design choices for such weak learners and investigate how using higher capacity learners lead to higher out-of-distribution performance and the trade-off with the in-distribution performance.